So let's have a look at the 2016 equilibrium question. It came up in question 7, another long question worth 50 marks. So we start off with state Le Chatelier's principle. So I have it written out already. We should know this by now. If a system in equilibrium is put under stress, the system will readjust in order to oppose or minimize that stress. And now they're going to move on and ask us to apply Le Chatelier's principle. So we're asked to predict and explain the conditions. So do we want a high or a low condition of temperature and pressure that would maximize the yield of the sulfur trioxide? Now our sulfur trioxide is our reactant. So basically is our product. So they're basically asking us, how do we make sure that the forward reaction is favored more and we get more of that product being produced? So let's have a look at temperature first of all. Now, we need to have a look at this delta H in order to help us understand what's happening with this reaction. So with the delta H, we know that that is an exothermic reaction. So we know that that forward reaction is exothermic. So if we want to make sure that the exothermic reaction is favored, that's the reaction that gives out heat, what we need to do is we need to decrease the temperature. So we need a low temperature in order to ensure that the exothermic reaction is favored. And in this case, the exothermic reaction is the forward reaction, which is going to increase the yield of our product. So this exothermic reaction, if we decrease the temperature, the exothermic reaction will be favored in order to give out heat and replace the heat that has been taken away. The second question then is, what happens with, or what do we need to do with our pressure to increase that yield? The first thing we need to be asking ourselves is, well, is pressure going to actually affect this reaction at all? Because we know that pressure only affects gaseous reactions. But we can see in the question we've got these little G symbols, so that indicates that everything is in the gas form. So it is going to have some sort of effect, or it might. If we have a look at either side of the reaction, we know that if we were to increase the pressure, the reaction or the equilibrium will shift in order to favor the reaction that produces the smallest number of molecules. So on our reactant side, we've got 3 molecules. And on our product side, we've got 2 molecules. So if we were to increase the pressure, the forward reaction will again be favored because we've got the smallest number of molecules being produced. So if we're going to want to increase the pressure. So the answer to that is we want a high pressure. So we want high pressure because it's going to favor the reaction that produces the smallest number of molecules. And that, in this case, is the forward reaction, which is what we want because we want to increase the product and produce the smallest number of molecules. Now, the final question that they're asking us is, explain why the temperature conditions predicted are not used industrially. So we met this in our case studies. So we had a look at the contact process and we had a look at the Haber process in terms of industrial case studies. And the main reason why we don't actually keep our reactions at a low temperature is if we think back to our rates of reaction chapter, if we decrease the temperature, we slow down the rate of reaction, which is not ideal and it's not economical. So it slows down the rate of reaction, and that is uneconomical in terms of industry. Okay. Part B then asks us to state and explain the effect, if any, the presence of the catalyst on the equilibrium yield of sulfur trioxide. So we know with our catalysts, a catalyst will not affect the yield. So it will have no effect on the yield, but what it will do is it will speed up reaching equilibrium. So catalyst doesn't affect where equilibrium lies, but it does affect the speed that equilibrium is achieved. So my writing went a bit wonky there. The final question then is our equilibrium calculation. So this one is slightly different to any of the ones that we've met so far, in that they give us the grams of our starting material, of our reactants, and they also give us the grams of our product at equilibrium, and they ask us to, first of all, write the equilibrium constant, and then they ask us to calculate the Kc under these conditions. So we've got 96 grams of SO2. We've got 24 grams of O2, and at equilibrium we've got 112 grams of the sulfur trioxide. So the first thing that we need to do before we even start thinking about our little table for this question is we have to convert everything to moles. And we're going to do that using our little equation, moles equals mass over RMM. Okay, so these grams are our initial, and this is telling us at equilibrium. Just label them all so that we don't get lost. So let's convert the sulfur dioxide to moles now. So we've got 96 grams. We divide that by the RMM of sulfur dioxide, which is 64. So I'll let you guys calculate that yourselves and check it yourselves. So we've got 1.5 moles. We have 24 grams of oxygen. So we've got 24 divided by the RMM, which is 32, and that's going to give 0.75 moles. And then finally our sulfur trioxide, so we've got 112 divided by its RMM, which is 80. Again, you can calculate that yourselves, and I should say when you're calculating the RMM in your exam, make sure you write out exactly how you calculated it. So for example, oxygen is 16 plus 16, because if you make a mistake, if you've written it out and the examiner can see where your mistake is, you may just lose 1 mark as a slip as opposed to losing 3 marks for making a full mistake. So just make sure you show all your work there. I'm just doing this nice and quickly for speed. Okay, so now we've converted everything to moles. Let's set up our table. So I'm going to rewrite this equation. SO2 plus O2 to give us 2SO3. So we've got our initial concentration, and that's going to be in moles per liter. We have our change, and we have our concentration at equilibrium. So we know that we have started off with 1.5 moles of SO2 and 0.75 moles of O2. But if we flick very quickly back to the question, this happens in a 50-litre container. So we want this to be in moles per litre. So what I'm going to do is I'm going to divide everything by 50 before I get started. It'll save me doing it at the end. So that gives me 0.03 moles of the SO2, and it gives me 0.015 moles of the O2. So they are my starting concentrations of my reactants, and I know initially as well I've got 0 moles of the sulfur trioxide. There's one more thing that we calculated, and that was the concentration at equilibrium of the SO3. So we were told that we had 1.4 moles of the SO3 at equilibrium, but again, that was in the 50-litre container. So let's convert that into moles per litre by dividing by 50, and that gives me 0.028 moles of the sulfur trioxide at equilibrium. So now that I've filled in everything that we were told in the question, let's fill in the rest of this table. And I think what we're going to do is work backwards this time from the concentration of the sulfur trioxide. So if we know that we've got 0.028 moles of sulfur trioxide, and we started off at 0, we know that we've had a change of plus 0.28 moles of the sulfur trioxide. In order to work backwards and figure out how many moles of each of our reactants this came from, we have to take into account the reaction ratio, and we can see that it's a ratio of 2. So if we have 2 moles of sulfur trioxide being produced, it has come from 1 mole of oxygen and 2 moles of sulfur trioxide. So we need to take that into account when we're figuring out how many moles, or what was the change in the number of moles of our reactants, or how many moles of our reactants were converted into our products. So if we get 0.028 moles of our sulfur trioxide formed, going by this 2-to-1 ratio, the number of moles of oxygen that comes from is halved. So what we're going to do is we're going to divide that by 2, and that's going to tell us the number of moles that oxygen, or the number of moles of oxygen that were converted into 0.014, that were converted into the sulfur trioxide. So that is the change. So that means I'm going to put a big minus there, because that means that we've had a change of minus 0.014. Now if we look at our sulfur dioxide and our sulfur trioxide, well, it's a 2-to-2 ratio, which is the same as a 1-to-1 ratio. So whatever number of moles of our sulfur trioxide are produced, that has to have come from the same number of moles of sulfur dioxide. So that's 0.028 moles. Now I can finally calculate the concentration at equilibrium in moles per litre of my reactants. So I've got 0.03 minus 0.028 of my sulfur dioxide, and that's going to give me an answer of 0.002 moles per litre. With my oxygen now, I've got 0.015 minus 0.014, and that's going to give me an answer of 0.002 moles per litre. And I've already calculated the 0.028 moles per litre of my sulfur trioxide. Now, the first part of that question did actually ask us to write the Kc. I just skipped over it and left it to the end. So the Kc for this equation, remember we've got our square brackets to indicate moles per litre at equilibrium. We start off with our products on the top. So we've got SO3 there, and it's raised to its coefficient in the equation, which is 2, divided by the concentration at equilibrium in moles per litre of the sulfur dioxide, raised to the power of 2 because we've got that 2 in the equation up there, multiplied by the concentration of oxygen. So now that I've written that, I have also calculated all these concentrations at equilibrium in my table up above. So I'm just going to fill in those numbers there. So I've got 0.028 to be squared divided by 0.002 multiplied by 0.01. That's going to give me an answer of 196,000, or you can write that as 1.96 by 10 to the 5. It's not necessary to change it into scientific notation, but if you're more comfortable with that, then that's absolutely fine. So that brings us to the end of the 2016 question. A little bit different compared to the questions that we've done previously, in that they gave us the starting materials in grams as opposed to moles, so we have to convert that into moles. And then again, we don't have the simple 1-to-1 ratio, we've got 2-to-1-to-2 ratio that we had to take into account as we were working backwards from our number of moles of our product. But other than that, it was a nice enough question. The next video then, we are going to move on to the 2015 question.